Come back to our course today. I'm proud to present Mr. Mahmoud Wagih. I would like to, before he starts with the presentation, I would like to give the short introduction. Mr. Wagih is a lecturer or assistant professor on the Royal Academy of Engineering in UK, RC Fellow at the University of Glasgow. He has published more than 110 papers across tactile, based, printed, flexible wire system, and so on. He received over 20 awards, including several IEEE Best Paper Prize and Best PhD in Europe in antennas and propagation. And currently, research activities are sustainable electronics design and investigation of the novel materials designed for this sustainability of the wireless systems and supported for the different projects. He is also a founder and also director of Eric's Watt Limitation, and he is also active. The activity is REACT, the Center of the Responsible Electronics and Circular Technology. This is a very short overview of this activity on Mahmoud. And yes, we would like to start with the presentation. The presentation with the title Responsible Electronics from Manufacturing and Radio Frequency Enabled Applications. And this talk should be introduce example for the high performance electronics fabrication approaches, taking a responsible approach and have to focus on the PCB level of the solution. That's for my part, and now we would like to share the screen with Mahmoud, and then we will start his presentation. I have 40 minutes for the presentation. After that, we have time for some Q&A. For my part, yeah, Mahmoud, you can start. I would like to close my presentation, and Jen.
Yes, okay. Thank you, Hans, for the introduction, and great to see so many people turning up to this webinar. So what I want to cover today is really about our work on sustainable electronics, but we're more broadly calling this here responsible electronics. And I will hopefully convince you that there is a difference and there is more of a role for electronics to play beyond just being more sustainable in their own right. So my name is Mahmoud Wagih. I'm based at the University of Glasgow, and I'm one of the co-directors of the REACT, or Responsible Electronics Centre, which is an initiative funded by UK Research and Innovation on how to work across universities, across industry and academia to develop more sustainable, more green electronic solutions and generally more technologies and eventually a green economy. Now, if you go and look at some of the existing published reports, whether that's in published papers or in industry reports, you'll find a lot of variations on how much ICT, digital technologies contribute to global warming, contribute to emissions. You will find some of those estimates coming between 2 to 6% of total greenhouse gas emissions being attributed to electronics hardware or the use of electronics. Now, whether or not this number is a big problem or a growing problem is something I kind of want to put in context of other technologies. Clearly, we need to do something here to reduce this number, or at least prevent it from growing further. But before I go any deeper in how we make electronics more sustainable, I've got a comparison of two things I've taken pictures of and I've interacted with in the last year. One of them, on the left-hand side, is a typical Internet of Things system. It has a PCB, multiple components, multiple integrated circuits, few surface mount components. And the other one is a cheeseburger that you can buy from a takeaway. They both cost approximately the same in terms of money. But when you think about the emissions from both of them, you will find that your burger, with assuming 100 grams of beef, might have perhaps 15 kilograms of equivalent carbon dioxide. And if you look at the electronic system, which provides a lot more functionality, it only has 7 kilograms of equivalent carbon based on assumed bill of materials for an electronic system. So perhaps the carbon emissions from electronics are not the highest, but that doesn't mean there's still other environmental problems that we need to be addressing, and I will discuss a couple of these. But the main role that a responsible piece of electronics could play is decarbonizing both of them. Whether we're generating electricity for transport, for energy in domestic use, or for manufacturing, this is all deeply reliant on power electronics. It's reliant on the components that will enable a renewables grid. Now, if we are moving towards a renewable grid, if we're moving towards more advanced power electronics, towards more advanced deployment of electrical grid everywhere, we are demanding a huge amount of resources from a finite amount of critical rare metals or CRMs or critical raw materials, and we might be depleting those resources. I mean, you see it in the news all the time about the metals and the imports from China and different parts of the world. There's the issue going on between the Ukraine and the US on the critical rare metals in the surface in Ukraine. There are lots of geopolitical challenges around these elements. There is environmental scarcity, and there is the fact that electronics manufacturing is almost entirely linear. We build our device, we make it using multiple high-value elements, and then we never reuse them again. And if we keep going this way, we won't be able to keep manufacturing high-performance electronics. If you look into a recent study that dealt with digital consumption, watching online content, watching videos, and scrolling through social media, we find that 55% of material consumption per capita, so that's in terms of minerals, for example, is associated with the hardware, the data centers, the edge devices that we use to interact with technology. And even though we could, in principle, decarbonize these emissions, we can shift to an entirely renewables grid, we don't have a scientific solution on how we can make electronics without consuming these materials. We don't have an answer on how we can reduce this number while maintaining the electronic functionality that we get from modern integrated circuits, from modern smart systems. So before we go into this, I'll walk you through how we can capture and document these numbers, and ultimately what happened in the end and how we are trying to reduce those numbers through both recycling and new device design and manufacture. The main framework that we use to determine the sustainability of electronics, well, among everything else, is life cycle assessment. So that's typically a cradle to gate, or perhaps in some cases cradle to grave analysis of the environmental footprint. And I'll show you the example here for wireless electronics because of my background. We have a large number of elements. We're looking at 400 plus chemicals that go in electronic manufacturing. So think, for example, the acids used in etching metals off chips, the chemicals used in cleaning and so on. That's, of course, in addition to the functional metals and semiconductors themselves. We then get to the point of manufacturing different devices that could be integrated circuits, could be using 3D printing and other more sustainable additive approaches, or generally by weight, the largest component of electronics, which is circuit boards or PCBs. And this manufacturing process is where we get our Scope 3 emissions, which are generally quite difficult to decarbonize because they happen overseas. We get to the point of fusing our electronics. We'll have a power consumption in the context of wireless communication. That will be the power amplifiers in the base station, the cooling associated with these, and of course the losses in every wire and cable in your system, which will reduce your ultimate efficiency. And that's where the majority of emissions come in. So we're looking at Scope 2 emissions that we, in principle, know how to decarbonize by moving to renewables. For example, in Scotland, most of our grid is based on renewable wind power. And in fact, we have more wind power than is needed, that the energy has to actually be wasted rather than being put to good use. So it shows that we need more than just generating energy to decarbonize that stage. Now, at end of life, we have the produced WEEE, or waste electrical and electronic equipment. And what we're trying to introduce is a way to circulate some of these components back after utilization, after aging. And the further you try and go left in this value chain, the more difficult it becomes to quantify the environmental footprint because it happens overseas, it happens in closed foundries, and it also becomes more difficult to decarbonize. So we've got very little control what we can do in how much silicon, germanium, and gallium and other elements you need in manufacturing a chip. But we've got things to do in how we reintroduce those devices back into circulation, back into the value chain, so that we can have more sustainable circular economy for electronics. So we did a study on consumer electronics. We published that towards the end of last year, and you can see the link in the slide. We looked at two examples, one of them being a low performance system, TV remote, and the other one being a medium to high performance system, smartwatch. That was based on the bill of material of a typical smartwatch, for example, an Apple Watch. And the analysis was all performed using industry standard LCA libraries available from Gabi or Sphera, as they're currently known. And we looked at what is the output across all metrics of the life cycle assessment. I'm only showing you the global warming potential because that tends to be the most pronounced one, the one that everyone is focused on from a decarbonization point of view. But the response is very much the same across other metrics, such as material use. If you don't recycle anything, you've wasted those resources, you've wasted these emissions. But if you recycle just the integrated circuits out of your system, that's more than 60% of the environmental footprint in your system reduced. No matter what else you recycle, because of a significant gap in how much it costs to make an integrated circuit in terms of carbon and materials relative to everything else, it makes very little difference what else you recycle. So all this tells us is that if you should do something to improve sustainability of a commercial electronics product, is find ways to recycle the ICs. That on its own can significantly reduce the environmental footprint. And of course, if you do this multiple times, you'll be able to bring that number down by however many times those devices were reduced, however many devices you didn't need to manufacture in the first place. We then dived a bit deeper and we started to look at more complex wireless systems. So take a wireless gateway, for example. You'll have an RF input that will be coming from a digital output, digital signal processing, and then you'll have the RF front end itself. And that's what we were interested in capturing in this study. You'll have an integrated circuit, typically power amplifier, so a very power hungry component. And then you'll have other components, maybe for phase shifting, switches, and of course filters and so on. When you take that system, we had to create our own model for RF PCBs because they tend to be made using ceramics, have quite a high amount of gold plating in the surface finish of a PCB, so they have a large environmental footprint. But then the largest value, again, it came from the IC. And you can clearly see that there's a gap in my y-axis because the IC is almost 10x more impactful than everything else within the same system. So it pushes us towards the same conclusion, is to reduce your ICs, use fewer of them in the first place. Once you've manufactured them into a system, allow them to have a second life through recycling and reuse. And I'm talking here about reusing the functional object rather than dismantling it for materials. If we wanted to look at trends in terms of emissions, so we went into the database for life cycle assessments and we looked at what information is out there on the increase in global warming potential per square centimeter of chip area. And what is the trend with going into more and more advanced nodes? Now, in memory applications and computing applications, we're always pushing towards a sub 10 nanometer. And you can see that there's a large increase, almost non-linear increase with the emissions, the number of layers in the process, for example, the reduced yield compared to legacy processors, all contribute to higher emissions coming from more advanced CMOS technologies. Now, in computing, that is a problem. But we also noticed the same trend in telecommunication. So with 5G, people wanted to move to millimeter wave bands around 28 gigahertz. With 6G, you see ideas around moving to D band and frequencies above 70 and 100 gigahertz so that we can have higher data rates, improved point-to-point communication, and of course support for more users. And this trend is going to come with an environmental impact. Even though we're going to shorter frequencies, smaller devices, the dies are not really shrinking, but we're still moving towards more and more advanced CMOS processors in order to be able to produce the high power levels and to integrate with the digital signal processing. So this demand on higher data rate communication, more advanced 5G and 6G network will have a negative environmental impact in terms of global warming potential per chip produced, which means we need to find ways of recycling these components or working with more sustainable devices, more sustainable semiconductor processes. There are other studies that were published after our work that looked at other materials, compound semiconductors like indium phosphide and gallium arsenide. And again, they do still have a large environmental footprint, even though they are using far larger nodes than CMOS. So now that we've established that we want to recycle ICs, what we're trying to look at is how we can use the package and the board to allow us to dismantle the circuit assembly at its end of life and enable recycling. So one of the visions we have within the React Center, and it's still work in progress how we get there, is we manufacture our ICs for a high-end application. And after several years of use, we can then put them through recycling. And that recycling would allow us to make a conscious choice. We can either take the functional units as they are and deploy them in new applications with less stringent requirements, which would accommodate an aged and slightly underperforming IC or out-of-date IC. And if all else fails, we'll have a small component that goes into material recovery and low waste materials. This means we can now take the offshore manufacturing of high performance chips and create almost an alternative supply chain, an alternative value chain that is local, that is more resilient, and of course that's more environmentally friendly, because we can now find uses for chips once they land in our market. In order to do this, we're looking at research on degradable PCBs, on degradable and reusable metals and degradable substrates in a subtractive, fully PCB compatible process, and we're developing that in conjunction with industrial partners. We're also looking at our own processes for PCBs and potentially on even unusual substrates. So we're looking at steel, which is one of the largest industrial wastes in the UK, being used as a substrate for high power or high temperature applications, which could potentially have lower environmental footprint compared to aluminium PCBs, for example. We're also looking at more blue skies research around fully biodegradable and zero waste approaches. So in this case, we've looked at zinc and fully degradable metals, and we've been able to fabricate them with really high resolution down to 10 microns, even right now, single-digit micron, in a semi-additive process that could be scaled over very large areas. So it could even be a solution for interposers and packaging technologies, and not just for board-level solutions. And the last thing we're looking at, which I'll show some examples of as well, is having fully recoverable systems where both the metals and the ICs can be recovered using low temperature metal alloys, which allow us to recover nearly 100% of all the material that went into making a high performance electronic circuit. So let's take the steel example. You can get steel, which is conductive. What we develop is we coat it with a thin layer of dielectric. So in this case, it'll be silicon dioxide typically. That's spin coated. And then once that's covered with the dielectric, you can now print your traces on the circuit. You can assemble your components, and at its end of life, you can put it in an ultrasonic bath. The components will fall off, the traces will delaminate, and you've got your substrate back. It's still clean. It still has a dielectric insulation. So you're now able to use it as a new substrate and manufacture a new circuit on the same process. It's based on additive manufacturing, so it already has lower environmental impact than etched PCBs. We can reuse the substrates, and the recycling is fairly straightforward. But if you have any experience with high-frequency electronics, you know that putting high-frequency circuits and components on metal tends to not work. So we had to explore a different solution to make these work for IoT applications, and that was building in the vertical direction. So instead of building antennas within the PCB, we started to adopt a design that's quite similar to existing monopoles that you have sticking out of consumer devices by printing scaffolds. Those scaffolds will only be printed in small parts of the PCB, so they don't compromise the thermal reliability or the mechanical reliability. And then they can be coated with silver. They're using degradable plastics like PLA, which then allow you to have standard wireless performance. You can now have antennas that have wide bandwidths. You can have reasonable gain across your bandwidth of the antenna. And we validated these in applications like a Wi-Fi sensor network for heart rate and other wearable monitoring applications. So that's one use case of high temperature, high power process, potentially one that could even be used in RF despite being across all signs unsuitable for high frequency applications. Now moving to a different approach, which is reusable metals and reusable integrated circuits. In this case, we're using gallium-based metal alloys, which can be liquid at room temperature or slightly above room temperature. We start by 3D printing microfluidic channels. So your resolution is only limited by how good your 3D printing or injection molding capability is. And then we will fill these microfluidic channels with liquid metal to form the interconnects of our circuits. Now, obviously, gallium is one of the most expensive elements. It's almost the same price point as silver, but we will look at the recycling in a couple of minutes. Your now empty channels can be filled with components, can be populated, and after your components are in place, almost like how you would deposit solder paste and reflow your PCB. In this case, we're depositing permanently liquid interconnects. Once you've got those liquid or malleable interconnects, you can now seal your circuits, and you'll have a functional wireless system which can then be used for different applications. And we validated that in a few signal generation and amplification use cases. Then it comes the end of life. The first point is breaking through your packages, destroying any glue joints that you have strategically located in positions where it doesn't impact performance. and then you would recycle your liquid metal, your component, through washing with a sodium hydroxide solution, which can then clean off the liquid metal. You can see the process here. You've got the debonded, unpackaged circuit. This will go through cleaning, and then at the end, you'll have precipitation of the liquid metal. It can be extracted. The additional solvents can all be evaporated, and the end result is full recovery of metals, full recovery of ICs, and we're able to put those back into manufacturing. The only waste produced is a dielectric. You can use plastics that are degradable. For example, PLA was one of the materials we used for prototyping. So that would give you zero waste at the end of life, or very low wastes apart from the glue and other non-degradable materials into a system. So to give you an idea of what we did, we built an example circuit of an RF power amplifier. This nicely combines DC power supply, medium temperature, medium current consumption, so several hundreds of milliamps. You can see the circuit here before it's been sealed. So the two large ground planes are fully filled with liquid metal. You can see the ICs with the liquid metal connecting to them. It's basically room temperature solder. And then when it's being operated without the cap on, you can see that it would withstand high temperatures. In this case, we're talking to 40 to 50 degrees when the amplifier is working at maximum power output. Of course, the large metal thickness, the large metal plane would also improve thermal dissipation. So it helps make this circuit actually cooler than the FR4 equivalent. We measured the performance before and after recycling, and we've tried multiple rounds of recycling for our circuits. And we can generally see that it's very comparable to the datasheet performance. At higher frequencies, you can see different ripple, and that comes down to the fact this is all manually assembled. So the height of the interconnects, the height of the metal traces is still not perfect. So we do have some problems with impedance matching, but the results, and hopefully the paper will be published soon, show that up to 3 to 4 gigahertz we can have wireless systems, and of course DC systems that perform really well with fully recyclable metals and components, all done near room temperature. In terms of how well this can be recycled, we've tried up to 10 recycling rounds, and there's no reason why we can't go higher. You can see some fluctuations in the weight of the sample, but over every stage, we're only losing 1% or less of the sample's weight or the useful weight through contamination or the addition of sodium hydroxide or undissolved solvents. And most importantly, the electrical performance was unchanged. Even when we recovered those slightly contaminated materials into the same process, we still got the same resistance, we still got the same insertion loss at high frequency. So it shows that the 1% mark for contamination or for material loss is still acceptable from a performance point of view. Now, there's also two examples that are still happening in the lab. They require a large shift in the electronics industry to be adopted. So my colleagues in the React Center are also looking at material recovery. We're also looking at how can we process existing e-waste without asking the entire industry to shift into our new processes, at least not immediately. And one of those approaches is fully chemical. So we're working with the University of Edinburgh School of Chemistry, looking at selective etching, selective recovery, and using organic solvents where possible to recover rare earth metals and precious metals from standard PCB plating, from packages, wire bonding specifically, to get our gold precipitating back. And we're looking at another high volume application, which is recycling the silver from photovoltaics. This is the main cost driver of a photovoltaic cell is the silver interconnects. And in this case, it's work done by our team at the Center for Medical and Industrial Ultrasonics, looking at how you can use cavitation, effectively using bubbles to lift off the metals at different rates and recover the silver and other precious metals from, in this case, PVs, but we're expanding this to other PCBs, printed electronics, and different devices. So this was a quick introduction into what we're doing with life cycle assessment, what we're doing with circuit recovery, material recovery, and recycling. And I'll now jump to the second part of the presentation and look at some wireless application. Why are we targeting wireless? And what are we doing in wireless that could fundamentally change things to a more sustainable approach? If you consider what wireless electronics are and what RF engineering is, this is a generic diagram I found online for the Internet of Things. And wireless technologies tend to play a fairly small role of just getting data from one point to the other. And if we zoom into even further, we look at what these arrows are actually made of, you will find generic RF hardware front ends that look like this block diagram. And at the end of them, we will find antennas, which again is a very small component in a fairly large system. Despite this, we go and look on IEEE Explore, and we find that there's a lot of people researching just this relatively small field and relatively specialist application. And we think there's more role for these components to play than just sending data from one point to the other, particularly in wireless sensor networks. So if we take our standard components, particularly those that are printed or manufactured using low energy processes, we run them at high frequency, and we look at them as a source for sensing and power, and both of them leading to sustainability. Today, I will focus more on the sensing aspect, but the power is a well-studied area, and that's where we're actually taking our research commercially on wireless charging, long-range wireless charging. But today, the focus is on batteryless and, in many cases, chipless sensing using RF interaction with different materials, and why this is important from an environmental point of view. Before I go any further, I've learned to add this slide because different people perceive RF sensing or radio sensing in very different ways. The most common definition, certainly the one that's commercially used and in deployment, is you send a wave and you receive a scattered reflection. The person or the item that you're monitoring, as far as you're concerned, is just a large lump of permittivity and conductivity that is changing in space, in distance, and potentially in time. In some cases, you'd collect a lot of data from this without a lot of prior knowledge about the operational environment. You run that into some machine learning and AI, in many cases without an understanding of what's going on in the data. And if you treat this as a standard image processing problem, you sometimes get what you want, but in many cases it can go terribly wrong. And an example I like to feature is the weather radar. Every year in the UK, you get migrating insects, which appear as rain because, as far as the radar is concerned, the permittivity is the same. So it's just see the big block of permittivity moving. It assumes it's a rainy day, but in fact, it's nice and sunny. So you can clearly tell that I'm not a fan of this approach. This is not what we are looking to do here. We're looking at devices that are aware of their surroundings and are specifically deployed for a sensing application. So we know exactly how the hardware will interact with its surroundings, how we can tailor those wireless sensors to their application. And when we deal with antennas, we're not just sending signals and looking at reflections. We're actually looking at them as circuit elements that interact with a measurand, circuit elements that will have a response in frequency that will change once it is loaded with what we're trying to sense for. This is not a new field. If you go and look on IEEE Explore, you'll find tens, if not hundreds of examples. If you go into the early 2000s and 2010s, you'll find a lot of liquid characterization. We've done some work in this area, but we question how practical it is, specifically because of sensitivities. You'll find that people like to detect water in different contexts because it has a very clear permittivity that could be observed. You'll find more water sensing in the context of smart agriculture. You will find indirect ways of monitoring water in food products and in living things like fruits and vegetables and watching how they change as they ripe, all in terms of permittivity and conductivity. And at this point, I don't think I've sold you on why we should be using this RF sensing approach. Why not just use a multimeter, or the equivalent of that multimeter is an embedded system with simple analog to digital converter? Why can't we just look at the change in resistance between all of these elements? And in many cases, the change in resistance might be enough. Now, the answer to this lies in the sustainability angle. If we have our sensors, which are basically changing capacitors or resistors or even voltage supplies that we want to convert into wireless data, the first thing we need is an analog to digital interface. And you typically need one per sensor. They have their own limitations and distortions. But once you have your digital data, you now start to have computing. Now, computing typically goes with memory, and if you break into any integrated circuit or microcontroller, you will find a very large portion of the area is going towards memory. And then finally, once you're done with your computing, with your processing, which in most cases is extremely basic and not even needed, you will put this into digital signal processing front end. It will then control an RF front end, similar to the block diagram I've shown earlier. And finally, you get your wireless data going out of your antenna. And to make this all work, you of course need some batteries to provide power to the system or other wiring. And typically everything apart from the battery would be living in a CMOS integrated circuit. And if you look again onto the chips, see how much area is being consumed. And there are lots of life cycle assessments that have investigated this in commercial consumer devices. You'll find that the computing, the memory have the largest footprint, simply based on the size and the advanced CMOS nodes they use. Now, the easiest thing to do with RF is to remove the battery and wireless power the system. This is a large portion of my research, and you can find a few talks and presentations online, but I'm not going to focus on this. I'm going to take this one step further, and I'm going to remove all computing, memory, and digitization from my system, and we would just look into having direct wireless sensing and identification. Without quantifying anything, you can visually see this will significantly reduce the environmental footprint of manufacturing and potentially the cost of the system, making it easier to deploy. So we started looking for applications, and we found RFID as a standard that's very pervasive, very well used, widely known. And we thought, let's start with this. They are simple tags, small ICs. They are very well recognized, and you can get the readers everywhere. And we tapped into the knowledge of how we made wearable components, how we made those washable so that they can be integrated into textiles. So we took those RFID antennas that have been optimized for wearables. They're fully encapsulated to be waterproof and robust, and we use them as ice sensors. Now, we chose ice because it's a nice binary condition. If you're running a wind farm, for example, all you care about is whether or not there is ice on your wind turbine or not. If this is a water pipe inside your house, it's either frozen or not frozen. So it's a fairly easy measurement to detect. The other interesting thing about ice is that it's a fairly low loss dielectric. In fact, it's almost completely lossless when it's just pure water ice, which means you can easily shift between water, which absorbs radio wave, to ice, which is completely lossless. So we could, in principle, improve the signal strengths by having freezing events, which makes them easier to detect. We modeled this in numerical software. We built a lot of prototypes, and we've tested them in the field, and the results were generally very promising. We can design the antennas that the gain of the antenna, the re-radiated power coming from an RFID tag, increases when it's frozen because of the properties of ice being lossless and improving the sensitivity. This gives us nice sensitivity of more than 10 dB, and you can see that's consistent across different distances and across different operation environments. And because it's a positive gain change, it's very immune to false reads. If you step in front of the antenna, you will reduce the signal strength because you're blocking the signal. The only thing that can improve the signal strength is if you put a large metal plate at an optimum distance behind the antenna. So we find that in most cases, we have very accurate detection. And in fact, the 10% that were inaccurate in our statistics were more about missing the reading when you have line of sight blockage with a metal object, say a car, for example. So it's quite a harsh environmental setting, and it shows that you can have reliable sensing, getting real-world meaningful data with just RFID tags, significantly reducing environmental footprint compared to a standard sensor. Now, ice is a fairly easy application because we've got permittivity that's readily available, but not everything that you want to sense will have a large permittivity gradient. So in some cases, you still need to rely on sensors or engineered materials in order to cause a change in permittivity or cause a change in conductivity, which allows us to make those simple, natively wireless sensors that don't need computing. We looked at temperature. It's one of the most commonly sensed parameter, and it's also one that's fairly easy to characterize and benchmark against other approaches. So we started developing our own thermistors. In this case, they were positive temperature coefficient thermistors, or PTC thermistors. If you're familiar with them, it basically means when you heat the device, you get an exponential increase in temperature. We made our own thermistors because we wanted to, A, make it more sustainable. So this was all done using low temperature molding. It's carbon fiber in a silicone PDMS filler. So something you can make in your garage. It doesn't need a lab. It doesn't need fancy equipment or high temperature evaporation and clean room facilities. And then we can also make it over very large areas, which is important if you're trying to make a wireless device. Now, why is this important when you're making a wireless device? Because we made the entire substrate of wireless components into a sensor. If you have a planar antenna, the entire surface that the antenna is deposited on could be made using our sensing material. Now, what this means is the power that you're injecting into the system gets a large portion of it absorbed based on the temperature, based on the loss in the substrate. Whatever doesn't get absorbed gets directly radiated by the antenna, which gives you radiation and signal packets that are directly modulated by temperature. It gives you a direct wireless readout that is entirely based on amplitude and is based on a very large sensitivity value. With all materials that have responses like this, there's a change in both capacitance and resistance, and we have designed our antennas in a way that both the resistance and capacitance are changing together. Now, why is this significant? If you've worked with thermistors, you know that beyond a certain point, they just behave like an open circuit because the conductive fillers are separated from each other, but they never disappeared. The conductive fillers are still inside the composite. They just moved further away from each other. This is the main limitation of thermistors, and that's for more than 100 years. They have always had a very narrow sensing range. Now, considering the fact that the conductive fillers are still within the compound, they're still within the composite, they've just separated slightly. That means in terms of electric fields, in terms of a non-contact method, you can still observe the change in the material properties over a much wider range than just observing it with a DC readout based on current running through the structure. So we can take a thermistor that is only useful for maybe 10 or 20 degrees of temperature change and increase that range by 4 or 5 times by observing the material properties at high frequency, effectively finding a new application for thermistors. Now, we mentioned that this should all be done with antennas. So we took our hot plate and infrared cameras into the anechoic chamber. People don't really like it when you tell them you're going to take hot heat sources into an anechoic chamber, but we did it anyway. And we measured the radiation as a function of temperature. Specifically, we wanted to measure just the gain and the amplitude because it makes it much easier to read the sensor response. And you can see here the radiation patterns over angle. No matter what angle you're reading the antenna's response at, there's a significant change in the antenna gain. There's a significant improvement because the material and the substrate is becoming lossless in terms of the antenna gain that we're seeing as a function of temperature. Now, it's very difficult to use this as a sensor that you give you 1 degree or sub 1 degree precision, but it could be used effectively as a detector, whether you cross the threshold of a certain temperature, for example, in a fire alarm or industrial process, particularly in a harsh environment where having multiple chips would fail. So we decided to take this further. We built a sensor. We've shown that it can work in an RF application. But our promise is we want to do everything in the RF domain. We want to reduce the chips, particularly from the tag. And remembering that our sensor is basically a capacitor, it's a variable capacitor, it's a variable resistor, we can then integrate it into an inductive readout system. We will have a reader which has a circuit that can sample reflections, and then we'll have a sensing tag which has a resonant frequency that is dependent on the temperature that our sensor is seeing. This is what the system looks like. We've got a very inexpensive reader, so it's an open source vector network analyzer that can look at impedance values and reflection values in a couple of hundreds of megahertz. This costs less than 100 euros, so it's a fairly inexpensive reader, even by RFID standards. And here you can see the very early prototype where the sensor was sitting on a hot plate, and then the reader and the sensor coil are connected to the VNA, and we're measuring the transmission between the 2 points. What this means is that now, as we are heating our device, we can get a sensitivity that is a function of the change in resonance frequency, and we are able to clearly observe a change in the resonance with increasing temperature, and observe that over a very large range of frequencies between 6 to 10 megahertz, giving us a high sensitivity that even a very low cost and simple electronic circuit can detect. It's a nice example of why you need bespoke materials, of why you need to co-design the material, look at its broadband electromagnetic properties before you design a sensor, because you can then get much higher sensitivities over other approaches, whether that's metals, ceramics, or even polymers, while maintaining a reliable read range that's very inexpensive and also very simple because we're operating at a low frequency. So 1 to 15 megahertz that could easily be read using the NFC range. Of course, we need adaptation to the hardware or the standards in order to be able to adopt this. But in principle, all the hardware needed for this could already be in your phone. This is good for individual sensors. And when you look in the literature, you'll find plenty of individual sensors using this approach. But when you take temperature as an application, you always find that arrays are interesting. If you're trying to monitor a wearable sensor or a biomedical related parameter, or even items on a shelf in a shop, you need multiple sensors. Typically, multiplexing is done with transistors. We wanted to be able to do that with just electromagnetics. So we designed our reader in a way that it can couple into every tag at a separate frequency, and that every reader could see at least 3 tags per signal port. So between switches, you can add a very large number of these sensors, and you could be potentially monitoring tens of these devices across a large area, all without adding transistors on the edge device that you might be throwing away. This is a demonstration here where we have a 3x2 grid. You can see the infrared picture and the hot parts where we've applied heat with a hot air gun. We can see a corresponding change in the resonance frequency that is the highest for the hot or the heated samples, and negligible change or leakage or cross-coupling between the unheated samples and the heated samples. And that doesn't affect the fact that our response and readout is fairly rapid. You can clearly see the distinguishment and the differentiation between the changes across different sensing elements across the array. This is a nice proof of concept that you can now have more devices. We can go beyond state of the art where you just have individual RF sensors being monitored at once. And it's one step closer to making this technology more practical, making it easier to adopt. It doesn't come without trade-offs. It doesn't come without a disadvantage. This comes at the expense of range, but we still think there are applications where even a couple of millimeters read range is good, because in many cases, the wireless distance is not large, your items are in contact, you just can't have electrical connections between the sensor and a reader. And we're now trying to expand this at A, longer distances, and B, more units than just 3 sensors. So I've made a lot of claims about RF sensing being more sustainable than DC. Luckily, there has been a study that's published on life cycle assessments of RFID, and it backs up a lot of our claims on why should we go chipless. This is, again, the output from the LCA done by a group in France across all metrics, and they're comparing the chip tag, standard UHF RFID, the chipless, the green line, and the light green for a standard optical barcode, which is just ink on a piece of paper. If you look specifically on the global warming potential, you can see that there's almost 60% reduction in this equivalent CO2 when we move from a chip to a chipless RFID, despite the tags being physically bigger. But the key one is the minerals use. There's almost 80% or more reduction in the rare earth metals being used in the minerals because of the fact we have removed the chip manufacturing from the equation, which can significantly reduce the environmental footprint. It obviously makes the devices easier to manufacture. You reduce your reliance on foundries. It reduces the turnaround time for new designs and prototypes. So hopefully this is evidence that we should be going more towards the chipless direction and using that to complement existing sensors and existing IoT networks. The problem is barcodes are still more sustainable, but we need to remember that barcodes are just IDs. Barcodes cannot provide sensing data. So the more data we can provide to users, for example, on localization, on environmental monitoring, and reducing food waste and other waste and high-value core supply chains, that could start to offset the environmental footprint added with electronics. And there are lots of examples in the logistics industry of people adopting RFID tracking, and that's significantly reducing the inefficiencies, reducing the distance that vehicles have to travel, which in turn would significantly reduce the emissions coming out of those systems. So all these activities, they come under the umbrella of a newly established sensors, REACT, or Responsible Electronics and Circular Technology Centre, that is being run by the University of Glasgow in collaboration with other organisations across Scotland. You probably caught it that we are interested in renewable energy and power electronics and in how we allow component reuse with digital passports, particularly using the RF techniques that we've discussed. Generally, it's a sustainable ICT angle as well. So we're not abandoning computing. We're looking at emerging technologies around neuromorphic or memoristic devices for AI. And from a hardware point of view, we're looking at IC recycling, PCB circularity, and I've shown a few examples of that. And ultimately, reuse and life extension before recycling. And if all of these fail, we've got techniques for recovering rare earth metals, for incentivizing recycling by allowing people to recover gold and other precious materials, which would make collection and recycling a lot more viable. The centre has a very large team, and I'm sure some of you would recognize some of the names here. So that's across electronics expertise, both in academia and industry. as well as material science, chemistry, and finally the business side of things. So we're looking at elements like green finance, responsible business and innovation, responsible business models. In other words, how could we make money out of sustainable electronics and sustainable systems? So with this, I've come towards the end of the presentation. I'd like to back that, just to wrap up, a lot of the work we've done here is backed by LCAs, and it's something we're trying to grow. So we're always looking into ways to find new data. This wireless sensing is an example of how could we design things to be sustainable in a different approach. And the last thing is to emphasize the importance of component recovery, IC recycling, and if all else fail, material recovery and material recycling. So that's it from me, and I'll be happy to take any questions you have.